So, what I'm going to start with today is going back basically to when we had t-tests, okay? And when we had t-tests, we had one variable and we had two levels of that variable, okay? And when we have an ANOVA, okay, what that is it's going to be where now we have a variable, but instead of just two levels, we have three or more levels of that variable, okay? And once we get to this, we basically use a different analysis because it's an easier way of finding out if there are any differences anywhere, okay? So what happens in analysis of variance is that we start talking about these extra variable levels, all right? So let's say that we have rats weight gain on various foods, okay? And typically when we would set it up, we would say, okay, well, here's, you know, brand A versus brand B. And that is your simple t-test, the difference between two means. But if I want to have a few more in there, there's a bunch of different brands I could try. So now I've got brands A, B, C, and D. In order to compare these using t-tests, right, I'd have to go A to B, A to C, A to D, B to C, B to D, and C to D. So 1, 2, 3, 4, 5, 6. I would instead need 6 t-tests to get all of my combinations. So instead of doing the 6 t-tests to find out if there's differences between specific things, what we do instead is we do what's called a preliminary test. We do one test that tells us if there's any differences anywhere. And if there are differences somewhere, then we go back and do a subsequent test to find out where they are. Okay? But rather than doing 6 tests one at a time, we just start with one big test. And that one big test helps us to know if there's a difference anywhere. Okay? And that test isn't that difficult. Now, the way that we're going to learn this is by a method that's called the components method, okay? And it is very similar to what's in your book. He just uses a slightly different notation, and I like the notation that I use better because it's a lot easier to remember, okay? So when we look up into doing analysis of variance, this first is that it's between subjects, just like we had a regular independent t. Okay? And there are several sources of variance. Okay? And so we have our A source of variance, which is also what we call our treatment effect, or this would be the brands of food that we're using. Okay? Now below that you see where it says subjects, and then there's this parentheses with an A in the middle. And the way you refer to that is called subjects nested in A. And that means that all of our subjects that we have, all of our rats or whatever, are inside levels of A. They're only getting one brand of rat food, and so they're nested in that particular brand that they're assigned to. And then the last part is total, and that's total variance. Now, the next thing over is something that you're familiar with. It's called degrees of freedom. Now, the key to doing a one-way and a two-way analysis of variance is if you can remember the formulas for the degrees of freedom, you will be able to bootstrap your way through the problem. Okay? So the first part that we have there is our source of variance, and the second column over is our degrees of freedom. Okay? Our degrees of freedom formula for the A term, okay, is A minus 1. And A is equal to the number of levels of the variable that we're considering. Variable. Okay. The degrees of freedom formula for the subjects nested in A, okay, is going to be AS minus A. And the formula for total is AS minus 1. The S is number of subjects in each level of A. And then 1 is basically just the number 1. So let's start with a problem. Okay, so we've got A, B, C, D, and these are our brands. Okay. And in notation of analysis of variance, this is going to be A1, A2, A3, and A4. Okay. And here's your food brand. So all right, so we've got 7 rats in each condition. And the rats get fed on this food for a week, and we see how much weight they gain. And these would be in pounds or whatever, let's say. So if we want to start off with our degrees of freedom, how many levels of A do we have?
4.
4. So what's 4 minus 1? 3. Okay. Now, we have 4 levels of A. How many subjects are in each of these levels? 7. So 4 times 7 is minus 4. Okay. And then what is 7 times 4? Minus 1? 27. So our degrees of freedom work out to be, this is the number of levels, minus 1, so there's 3. This is the number of levels times the number of subjects in each level minus the number of levels. And then the last is the total number of subjects minus 1, the total degrees of freedom. right? And so what happens here is the 27 is actually 3 plus 24 equals 27. And so if those numbers don't line up for you, then you've made a math error somewhere and you need to fix it. So the rest of our source table, okay, is made up of a term we knew, the sum of squares, which we had when we did t-tests. Something that's called the mean squares. And we had mean square error, right? That's what we divided by. And then we have what's called the f-test, okay? And for a one-way analysis of variance, we actually don't use these blocks right here. They're not used. Yep.
What is the T?
Total.
What is the S then?
What S?
The SA. Above the T.
S is the number of subjects in each level of A. How many subjects are in each level of A? Are you asking me what the...
I don't know why they're different.
What is different?
Why the S and the T are different.
Why the what is different?
I don't know why the S is different from the T. I don't understand.
It's a total number of degrees of freedom. So I don't understand what you mean why the S is different.
I'll figure it out as we go.
How many subjects are in each level of A? How many subjects are in each of these boxes?
Not 24.
Oh my God.
It,
Answer my question. How many subjects are in each of these boxes?
6.
Count again.
Well, there's 6 for each box, so...
No, there's not.
There's
Count
not.
again.
It's 7.
There's 7. So these are going to become little formulas, all right? So A is the number of levels of the variable. How many levels are there variables here?
4.
4. So what's 4 minus 1?
I understand now.
Okay? And then the next one, when we do this AS, okay, so 4 levels times 7 subjects, 28 minus 4.
Makes a lot of sense. Thank
Got
you so
me?
much.
Jam. Okay? Like, don't overthink it. You guys are too smart for this class now. Don't overthink it. You've been doing that since the beginning of this class. Am I right? It's so much easier. You guys come in here with your math phobia and you freak yourselves out. It's easy. All right. So now we've got our degrees of freedom. Now the thing is, the degrees of freedom formulas are really going to be very useful to you because they're going to help you to figure out how to do the rest of this problem. Okay? Using the components method, what you have to do is you're going to get something that's called necessary terms. Okay? I'm going to use a different sheet of paper here. And our necessary terms are going to be based on the terms that are in our degrees of freedom formulas. So if you look at this in the front, right, we're going to need an A term, we're going to need an AS term, and we're going to need a 1 term. Okay? So we're going to need an A term, we're going to need an AS term, and we're going to need a 1 term. Okay. And the reason is because when we want to figure out our sum of squares, we're going to use the same formulas as the degrees of freedom, only instead of A being the levels of the variable, A is going to be the value of the A necessary term. AS is going to be the value of our AS necessary term. Okay? So if you can remember the formulas for the degrees of freedom and this one more part that we're going to do right now, you can bootstrap yourself through the whole entire problem and you won't get stuck. Okay? So we have A, AS, and 1. Now, remember how when we were doing this before, we were getting the sum of the x's, the sum of the x squareds, and we can get a mean for each of these columns. Okay? So let's do that next. Okay. So if my n is 7, my sum of the x's, I got 12. I got 24. And I got 1.71. Okay. Another 12, another 24. All right, so now here's my values with this, okay? And so these are sort of what we've had before, our sum of the x squared. Now, we're going to use these values to get our necessary terms, okay? So when we look at the necessary terms for A, okay, in here, I say to get your necessary terms, and we're going to get A, AS, and 1. Your A term is going to be your group sums squared divided by the number of scores in each group and add it up. So just keep that in mind and let's do it, and then it'll make sense. So we need our group sums, the sum of the x for each group. Okay? So our group sums, so you're going to go, our A term equals 12 squared plus 12 squared plus 29 squared plus 24 squared. And we're going to divide that, and since there's always equal n, how many, Miss Kelly, how many people are in each group?
7.
So what are we going to divide by?
7.
Excellent. 7. Okay, so that's our A term. So how I do that in my calculator, go pretty fast, because you can just do 12 squared plus 12 squared plus, again, it'll be 288, 29 squared plus 24 squared plus, and if you do equal, it'll be 1705, and then you go divided by 7 equals. So it's going to be 243.57. And this is going to be our A term. Okay. So our next necessary term is our AS term. Now, if you look at the AS term definition, it says we're going to take the individual scores squared and we're going to add them up. And so what that really is it's if we went 1 squared plus 2 squared plus 1 squared plus 2 squared plus 3 squared, blah, 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 to 3 squared plus 3 squared plus 4 squared. But when we entered these in the individual row, in the individual columns, we already did that part, right? It's actually here. So 24 is 1 squared plus 2 squared plus 1 squared, blah, blah. This 84 is 3 squared plus 3 squared plus 4 squared. So if you want to go the sum of the x squareds over here and just add these up, okay, then that'll give you your AS term. So you can go 24 plus 24 plus 125 plus 84. And in theory, we're dividing by 1, because what does it take to get 1 squared plus blah, blah, right? So this 24 is as if each of these values was squared individually and added up, okay? We're just cheating a bit because we already sort of did it in the calculator, so all we need is these 4 values, okay? So here, let's just add that. So we've got 24 plus 24 plus 125 plus 84. All right, so I got 257. Okay.
Where does the 1 come from?
If we were to, so here, this 7, right, it comes from adding up these and then squaring it. So we add up 12 and square it. So what it took to make that 12 was 7 numbers, okay? But really what this 24 is if we went 1 squared plus 2 squared plus 1 squared plus 2 squared plus 3 squared plus 1 squared plus 2 squared. And what does it take to get 1 there? 1. This is one animal, one animal, one animal. And so if you did it all the way, right, it would just be divided by 1, each item, okay? So now the last part that we get is what I say is one big number, sort of. And what this is it is the sum of all the numbers, the sum total of all the scores, squared, and then divided by the total number of scores there are, or the total number of people in the experiment, or the total number of rats in the experiment. Okay? So if we were to add this up, okay, we've got 12 plus 12 plus 29 plus 24. So 24 plus 24 plus 29 plus, so I got 77 total. The sum total of all the scores is 77. So this one would be 77 squared. And how many total participants, rats, subjects are there in this experiment? Somebody said it. Dave, is that you? 28. Okay. So you go 77 squared divided by 28 equals 288.75. All right. So the hardest part of this problem we've already done. The first hard part is you need to memorize the formulas for the degrees of freedom, and then look at your data and get those values. The second hardest part is to get your necessary terms, and so you have to remember what goes into each necessary term, okay? And how I just do it is if you set up your thing like this, okay, you're going to go this squared plus this squared plus this squared plus this squared, and then divided by however many it took to make that number. So individual squared. Squared added up, because there's your x squared. And then the last piece is everything squared and divided by the total number in it. If you can remember that piece, the rest of it will be very easy. Okay. So the next thing that we're going to do is we're going to get our sum of squares values. There's a sum of squares for the A term, sum of squares for the subjects nested in A term, and a sum of square for the total. Okay? Where did I tell you the formulas were to get these sum of squares? They're the degrees of freedom formulas. And where are the values that go with that? What are they called? Necessary terms. Okay? So, what we're going to do now is the sum of squares for A, that formula is A minus 1. So we'll go 243.57. Something's wrong.
I think
I made an error here.
your 1 I think should be 211.
Yeah,
211.75. Okay. Do you know how I know there was something wrong? Huh?
I said you're smart.
No. Not smart.
Did you add something?
Because remember how I told you in a correlation, which some of you violated that very badly? What's the highest value a correlation can be? 1. Analysis of variance can never have negative in it, ever. So when I looked at the A minus 1, I was going to get a negative number. I knew I made a math error. Okay. So you can't have a negative number. So then I would go back and I would double check. Where did I make a mistake? So let's go 77 squared divided by 28 equals, yep, 211.75. Okay. Now I'm good to go. So 243.57 minus 211.75 equals. You're smart. I appreciate that, though. Tell my mama. I did the stupidest thing over the weekend. Just so you know, I won't give myself a concussion in my house. I was trying to put up a garage door opener, and it weighed more than I thought, and when I let that last bolt out, it like fell down, and it was still, the pole was still attached to the garage, and it swung around and like hit me in the side of the head and knocked me right off the ladder.
Oh my God.
And then you know what happened next? I got up super fast and looked and saw if anybody saw me. And of course, my neighbor saw me.
Are you feeling okay?
No, I got a headache. That's what's Sunday. And then my cat goes, "You dumbass." She's very judgmental, that cat. You could just tell. She just looks at you. Stupid. I knew that was going to happen. Because I didn't want to pay somebody $99 to put it up. So, but I appreciate you thinking I'm smart. I'll tell the neighbor that. Yep.
This is super before this, but what's the TX with the A?
Treatment.
Oh, so it doesn't really matter.
It does. It's just a short term for treatment effect. So it's what we're doing in the experiment. So where the A term is going to be, what is the difference between the foods? What is the difference between the brand of food?
Do we have to write the TX when we write A?
No, you're going to write food,
Oh.
something like that. Okay, it's just a habit.
Okay.
All right, so our next term is what? Sum of squares, subjects nested in A. There's no B.
That's what I meant.
That's what you meant. B? No. Subjects nested in A. And so that formula is AS minus A. So our AS term is 257 minus 243.57. equals 257 minus 243.57. My neighbor saw me. I'm never going to live it down. She lived across the street from me for like 17 years. She's never going to die. It's going to be like one of those things. Because you know what? She didn't say, oh, are you all right? She went, that's what she did. Oh, are you okay? Because, man, that looked like that hurt. Yep. It hurt. Thank you. Appreciate that. She said, well, I knew you were okay because you popped right back up like a weeble. But, you know, there you go. Like, looking at it now, I can't see how I ever thought that was going to not happen. Just physics alone. But, whatever.
That's why you're a psychology professor.
I know. I'm not stupid. I'm just highly specialized. That's what my physics professor used to say when his wife would say, how did you ever think that? Listen, dear, I'm not stupid. I'm highly specialized. 13.43. So now we only have one more piece, okay? And it's our sum of squares total. And that's going to be our AS minus 1. Okay? So that is 257 minus 211.75. All right, 45.25. All right, so now we have the three values that we need. So let's put them in. This table is called the source table. And you've seen this table. You just didn't use it because we looked at just the t-test. But you'll see this same source table in that t thing. You just don't usually look at the f. So our sum of squares for A is going to be 31.82. Our sum of squares for subjects nested in A is 13.43. And our sum of squares total is 45.25. Now, look at this. Is there another place I can check to see if I've made a math error?
I don't know, they make 100.
If I add these two and they don't give me that, I've made a math error somewhere. Okay? Just like 3 plus 24 is 27, 31.82, 13.43 is 45.25. Okay. Now, our mean squares formulas, mean square for A equals the sum of squares A divided by the degrees of freedom for A. So 31.82 divided by 3. .6066, so 10.61. And then we need our mean squares for subjects nested in A. And notice this is shaded, and these will be shaded for you in your test or whatever, and then in the analysis variance printout, they're just not there. So is 13.43 divided by 24. Equals 0.5595. So let's go 0.56. And then our F value is the mean square A divided by the mean square subjects nested in A. So it is 10.61 divided by 0.56. equals 18.95. Typically, any F that you get over about 6 will be significant. But we find it exactly. Okay. This is our F table. Okay. And our F table is, we have two values. It says, the top part there says degrees of freedom for the numerator, and the side left is the degrees of freedom for the denominator. And our top row of each one, okay, is the top is 0.05 and the bottom is 0.01. And this is always two-tailed in analysis of variance because in the real world we'd be making predictions based on some theory that we thought about the data, but since there's all different ways, you know, you have more than 2 data points, one can be higher, one can be lower, whatever. So, and this is a preliminary test that's just looking for differences anywhere. Are any of these means different from any others? So on our numerator, right, what's the numerator in a fraction? Top. So the numerator is going to be 3 degrees of freedom, and the denominator is 24 degrees of freedom. Okay. So here we would say our F crit with 3 and 24 degrees of freedom, alpha is 0.05, equals. So numerator 3 and 24 degrees of freedom. This is the next page here. Okay. And we're going to do 0.05, so it's going to be the top there, is 3.01. Okay. And it's just absolute value. Because remember, there is no negative in an analysis of variance at this point. Okay. So our 3.01 and our value got to be 18.95. Okay. All right. So we know that there's a significant difference between these means somewhere. And now what I want you to do is I want you to look at your data here. And if we were to guess which brands were different from each other, okay, here's brand A, brand B, brand C, and brand D, okay. Let's think about this. Well, under which brand did they gain the most weight? Okay. Under which brand did they gain the least weight? A and B. And A and B, is there going to be any difference between A and B? No. No. What about difference between C and A, C and B? Probably, right? What we don't know, and it's most likely that D will be significantly more weight than B and A. But what I don't know for sure is, do we have enough difference there between C and D? Right? So when you describe what's happening in your experiment, when you've got more than 2 levels, you want to think about it in terms of, like, what would I want to know if I was a veterinarian, or what would I want to know if I was a cog-neuro person in a rat lab, right? And my goal is to have the rats gain weight as fast as possible. But remember, everything costs money, right? So C might make them gain the most weight, but there's a big price difference between C and D, let's say. And so if there's no significant difference between C and D, then I would just might as well buy D, save my money, right? We're looking for significant differences. Because if I ran it again, and remember, if it's not significant at the 0.05 level, you know, and especially if it's close to being significant but not, odds are that if I ran the experiment again, I might not get significance that time on between those two. So you see now that an analysis of variance is a preliminary test that tells us there's difference somewhere. But we don't really know which of those brands are significantly different from each other. And so we have to do what's called a subsequent test. Okay? So I like the best one I like, because you can do it by hand, is something that's called the Fisher's LSD. And I think it's Fisher's LSD. Okay? And the LSD stands for least significant difference. Okay? And what that means is, and between these means, what is the smallest amount of difference between them that we get to say they're significantly different from one another? Significantly better, significantly worse, whatever. Significant. The least significant difference that lets us say they're significantly different. So when we get to this point, we go back to our means. Okay? And what we're going to do is we're going to see, well, what is that value that makes them the least significant difference? And so for this, there's a formula that we use. Okay? And this is it. Okay? And now we're going to go back to our t values. And so we're going to do t crit. Okay? Times the square root of 2 times the mean square error term. And we say n, and the reason we say n is because this actually varies depending on, you'll see next time we do, when we expand on this and do more than one variable, not just one variable with multiple levels, when we do two variables. So let's break this down. We want, in this particular one-way analysis of variance, the mean square error is what we call our error term. And if you go back here and look, mean square treatment divided by mean square error, that's basically a t-test. It's the difference between the means divided by the standard error. And that's what your F value is. Okay? If I only were to have 2 levels instead of 3 or 4, mean square divided by the subject's nested in A, the mean square error term, will exactly equal a t-test. Okay? That's why whenever you did a t-test, you got the F's source table as well, even if it was only 2 levels. So, in the same way we have it here, so what is our t crit? It's going to be the degrees of freedom associated with the error term. And so how I put treatment here, you can put error here. That's the error term. That's our standard deviation. That's the difference within the means. Okay? The smaller this number is, the better off we are. Just like the smaller our standard deviation was, the better off we were. So here, we can go look up, find out what our t value would be. All right. Now, you do this to the same degrees of significance as you did the original F test. Okay? So, the original F test we said was at alpha equals 0.05. It's always going to be two-tailed because an F test is always two-tailed. So we've got a two-tailed, alpha equals 0.05 with 24 degrees of freedom. Okay. So two-tailed, alpha equals 0.05 with 24 degrees of freedom is 2.064. Okay. And it's just absolute value, 2.064, so it's not going to be positive or negative. Okay. And we're going to go 2 times our mean square error term, and our mean square error term is 0.56. And our n is the number of rats in each condition. So it's going to be 7. Okay. So I always do this sort of from the inside out. Go 2 times 0.56 divided by 7 equals square root equals times 2.074. I might have made a mistake. Did you guys get 0.8256? Yep. Okay, so you can say 0.83 is good enough, really. All right, so now I know that the least significant difference is going to be 0.83. So now I can go back and I can see that anytime I subtract these means from each other and that difference is larger than 0.83, and it doesn't have to be positive, negative, whatever, you just look at it. It's just an absolute value of difference. If that value is 0.83 or higher, then you have significance. So one way that we do it where it's easy to make sure we don't miss anything is we sort of set up a little grid, right? So I had 4 things. So here's my brands, A, B, C, and D. And here's A, B, C, and D. And I'm just going to make a grid, and I only have to do like one side of it. That's going to be my difference between the 2 means. And so for ease, I sort of go back here, and I can make it easy. I can go A is 1.71, B is 1.71, C is 4.14, and D is 3.43. So let's see which of these are significantly different, right? So A from A is nothing. What's the difference between A and B? 0. All right. What's the difference between A and C? So 4.14 minus 1.71 is 2.43. So A and C, 2.43, which also will be B and C. What about A and D? So 3.43 minus 1.71 equals 1.72. And that'll be the same as B and D. And now let's see the difference between C and D. 4.14 minus 3.43 equals 0.71. So what's our minimum difference? So is 0.71 in the region of rejection? No. Okay. All the others are significantly different from each other except for A and B. Okay. So I would put little significant stars here, meaning that these are significantly different. That's not, and that's not. Okay. So you see now, yep.
Sorry, how did you get the points for that chart?
What
You add them
points?
to 23?
Huh?
You add them to 23?
No. What's the difference between A and C?
Oh, okay, all right.
Right? So this is going to be our difference chart, just the absolute value differences between the means. This is how we actually tell what's significantly different from one another or not. So remember, the analysis of variance tells us we have a difference somewhere. It turns out that 4 of them are different, right? There's 4 sort of differences that are there, but there's 2 that aren't different. So there's no difference between A and B, right? And there's no difference between C and D, but all the rest are significantly different. So now I want to think about how I would like to write this up. And in the same way that I sort of have these heuristics, you can do however you want. I sort of say, what would I want to know if I'm a physician or a veterinarian buying food or whatever? And I would say, well, what is the most weight gain, right? So I would probably say that the brand that had the most, or the rats that had, I guess probably, the rats that had the most weight gain ate brand C. Okay. However, there was no significant difference between brands C and D. What we mean by significant difference, it means that we could have got that big of a value just by chance or whatever. It's not significantly different. Okay? That's not a big enough difference to warrant it, right? To warrant buying one over the other. However, the others are significantly different. So then you could say, however, there was no significant difference between brands C and D. Okay? Then you could say brands C and D both caused significantly more weight gain than brands A and B brands A and B were not significantly different. Okay. So in the end, I would say as long as there's no price difference between C and D, I'd buy C. But if there's a big price difference, there's no significant difference between C and D, so I'd probably just buy whatever the cheapest is. Yep.
So the F-crit number tells us if there's a significant difference, and if there is, then we do the T test to find out what it is.
Yeah, it's the Fisher LSD, which is based on the t-test, yes. So the analysis of variance is what we call a preliminary test. The Fisher's LSD is a subsequent test. And that is the one that's really the most important to tell us where the differences lie. But remember how long it took you guys to do a t-test and everything? When we've got 4 levels, we don't want to do this 6, 7 times. We just want to do one test to say, is anything different somewhere worth another look? So that's what we do. Okay. Now, this gets quite easy when we start looking at in the computer.